All right, everyone. This time I would like to welcome Matt Miller from the SWI Security Science team. So welcome, Matt.
Thank you. Thank you very much. So thanks, everybody, for coming out. Thanks to the BlueHat folks for putting on this conference. I think it's a really valuable vehicle for delivering the type of information that I'm going to be talking about and that other people have been talking about. So the focus of my talk, the title's Mitigations Unplugged, but really what I'll be talking about is taking you on a technical journey through the mitigations that Microsoft has developed and integrated into the platform and offered through the compiling tools and other things like that to help you better secure your applications and things of that sort. So there are three primary questions that I'm going to focus on answering in this talk. First of all, if you have no idea what a mitigation is, that's okay. I'm going to answer that question. I'll explain what some of the acronyms are, like GS, DEP, ASLR, what all these things are, how they actually work, and what types of problems they're actually trying to solve. I'll also go through the evolution of these mitigations. So I'll show you, here's the problem that they were trying to solve. Here's how attackers were taking advantage of vulnerabilities. Here's how the mitigation works. Oh, and here's how the attackers actually maybe bypassed that mitigation and what steps Microsoft took to make it so they couldn't do that in the future. And I'll also give you a glimpse of things that we might expect to see in the future in terms of mitigations within the platform and beyond. So first of all, what are the motivating factors for mitigations? If we think about it, I think most of the people in this room will agree or have seen that software vulnerabilities are a very real and very serious issue. They cost lots and lots of money to not only Microsoft, but third parties, and everybody else out there suffers from vulnerabilities that exist in software. They can be costly to fix, they can be really dangerous, and frankly, they can be hard to find. There has been significant advances in static analysis tools and other tools that help us actually try to identify bugs, but the fact remains that these bugs can still be fairly challenging to spot. Now, what we have out there is these vulnerabilities provide an avenue for exploits to take advantage of them, to gain control of a system, to access resources that they otherwise shouldn't be able to access, and do all sorts of malicious things. Over time, there have been reliable techniques that have been developed to take advantage of vulnerabilities. And these are generic techniques. So let's say you have a stack-based buffer overflow. There have been techniques that have been developed that will work pretty much cookie cutter across any number of different vulnerabilities, so long as they meet a certain number of requirements. And since these reliable techniques have been developed and refined and made very reliable, there's very often limited expertise needed to take advantage of these vulnerabilities to actually compromise the system. So what this means is we need to have some mechanism to provide broad protection against the exploitation of software vulnerabilities. And in effect, we need mitigations. So what are mitigations? And really kind of the key insight here is that if we think about vulnerabilities, if vulnerability exists in code, but it can't be exploited, in other words, it can't be used to execute code or compromise the machine or access resources, then that vulnerability sort of becomes a reliability issue. They aren't actually able to take advantage of it to gain access to the things that they want to gain access to. So in that sense, vulnerabilities that can't be exploited are often less risky. So what we want to do then is we want to have countermeasures that will provide a mechanism to prevent or reduce the reliability of the exploitation techniques that have been developed such that we can lower that risk and make it less likely that somebody can actually take advantage of a vulnerability to execute arbitrary code. And the nice thing about this is that if we develop these mitigations, not only can we provide protection for known vulnerabilities, but we can also provide protection against vulnerabilities that we aren't even aware of. So that can be really valuable for us, and it helps not only Microsoft, but it also helps the third parties protect their software by having these generic mitigations that aren't tied to a specific vulnerability. So now we're going to start shifting gears and start talking about how these mitigations have evolved. And if you think about it, the question might come to your mind is, what came first, the mitigations that I'm going to be talking about or the exploitation techniques that they're trying to counter? Well, in fact, most of these mitigations try to counter known exploitation techniques, or they try to counter certain assumptions that exploitation techniques make in the general sense. So in that sense, exploitation techniques came before mitigations, and mitigations are trying to solve and counter those exploitation techniques. So how I'm actually going to show this evolution, as I alluded to earlier, is I'm going to explain in a technical sense how people actually take advantage of vulnerabilities, how they work, how the mitigation tries to counter those assumptions that those techniques make, and how the attackers have adapted to try to defeat or bypass these mitigations over time. So with that, let's start diving into some of the technical bits here. So we're going to dive straight into the low level. If we think about on x86, we have a stack frame. And the stack frame is traditionally composed of some arguments that are pushed onto the stack, the return address to return back to the caller, the saved frame pointer, and local variables. This is kind of the general structure of a x86 stack frame. And on x86, the stack grows towards lower addresses. So with this in mind, now we can start talking about the first and sort of most well-known exploitation technique. This exploitation technique is called a return address overwrite. And what this technique involves is you have some stack-based buffer. If we look in the bottom right-hand corner, we see we have a function called f. It has a local variable buff, and it has a stir copy that could be potentially unbounded into that local variable. So what happens if the input pointer is more than 256 characters? Well, now we start writing past the end of the bounds of buff. We start overwriting the saved frame pointer, saved EVP. We overwrite the return address, overwrite arguments, and on up the stack into previous stack frames. So the way that attackers can abuse this is they can overwrite the return address with some other address, maybe the address of their malicious code that they've injected into the address space of the process. They can overwrite it with whatever they want. And in so doing, when this function returns and trying to transfer control to the function that called it, it instead transfers control into attacker-controlled code. And now they're able to execute arbitrary code, gain access to resources that they should be able to access, compromise the machine, what have you. You know, sky's the limit at that point. So with this in mind, the first mitigation that we see is stack cookies, /gs, guard stack. What this mitigation tries to do is it inserts a cookie into each stack frame, or the ones that are where it needs to insert a cookie. And the purpose of this cookie is to provide sort of a marker such that if there is an overflow, we can detect that overflow and prevent returning into code that we shouldn't be returning into. So the way that this works is when a function is called, a cookie is first inserted into the stack frame, and it's inserted prior to the save frame pointer, return address, and the arguments. So it's basically in between the local variables and the other data that exists on the stack. At the time that the function returns, we're going to make sure that that cookie is still the value that we expect it to be. And by the way, this is a cookie that the attacker shouldn't be able to guess. That's the thing. The cookie is a secret. And if the attacker doesn't know what that value is, if they do overwrite it, then we'll be able to detect that some kind of overwrite occurred and prevent arbitrary code execution. So when we have a buffer overflow here, the overflow overwrites that cookie with whatever attacker-controlled data. We validate it. We see that it mismatches, and we terminate the process or take whatever steps we need to make sure that the attacker can't gain control of code execution. So this is how the mitigation worked out of the box and still works today. So what the attackers realized is, well, what happens if we overwrite, say, a parameter or maybe some other variable that is used prior to the time that the function returns? So in this example, we have two parameters that are passed into this function, in and out. The first one, we have a stir copy that copies into our local variable buff. And that could overflow. We could write past the bounds. And when we do, since the way our stack is set up, we overwrite the save frame pointer, we overwrite the return address, we overwrite our parameters that were passed in, which includes the in and out pointers. So when that second stir copy happens there into the output pointer, that could be a pointer that the attacker specified. It could be anything. And in essence, the attacker is able to write anywhere they want to in memory. And that happens before the function returns. So in this case, GS didn't help us. So the mitigation to this was to improve GS and have a little bit more intelligent layout for the stack. And the way that this works is now GS will position fixed size arrays, such as that character buffer that we've been talking about, and it will position them so that they're directly adjacent to the stack cookie. And they'll move things like the arguments that are passed in. They'll make safe copies of those arguments. And they'll also move things like pointers or other interesting variables such that they precede the arrays on the stack, such that if there is a stack-based buffer overflow in one of these fixed-size buffers, it's not possible for them to overwrite any of the parameters. It's not possible for them to overwrite any pointers that exist on the stack. And really, all that they're left with is being able to, they're forced to overwrite the GS cookie. So this allows us to have a more safe assumption that the attacker won't be able to overwrite things that might be used before the function returns. So that's how GS worked, but the attackers are smart, and they figured out another way that they can actually exploit stack-based buffer overflows and execute code before the function returns, even if it has GS, regardless of the fact. And what this does is this technique is called an SEH overwrite. Stands for Structured Exception Handler Overwrite. And if you're familiar with the way that structured exception handling works on x86, the gist of it is that when a function executes and it has some exception handling, it has the try except block that you see in the code. What happens under the hood is the compiler will insert some code that will push what's called an exception registration record onto the stack. And that registration record consists of an X pointer and a function pointer, which is illustrated here as the handler. And what this does is this basically chains a number of exception handlers together such that if an exception does occur, each of these exception handlers can be called and given an opportunity to handle that exception, to recover execution, or do whatever they need to do. So that's the normal course of operation. Now, intro a stack-based buffer overflow. What happens now is, since this exception registration record was pushed onto the stack, now the attacker has the opportunity to overwrite the next pointer, overwrite the handler, overwrite anything else that exists on the stack. And if they're able to cause an exception to occur before that function returns, then what happens is the handler that they've overwritten with whatever arbitrary values they control will be called as a function. So in essence, the attacker is able to have code or an address that they control to be called prior to the GS cookie being checked or any of these things. So this provides an attacker with an avenue to defeat GS, or it works even if GS isn't present. So this diagram here kind of provides a little bit more of an illustration about how this is traditionally set up. On the left-hand side, you see that we have a normal SEH chain. And this is a linked list. So we have a couple different entries in there for various exception handlers, and that linked list is terminated with a -1, symbolic -1, for an X pointer that says this is the end of the chain. Now when we have a corrupt exception handling chain, what ends up happening is, as I mentioned, the handler will be pointed to an address that the attacker controls. It could be anything. In this case, what ends up happening is most of the time an attacker will overwrite the handler with the address of pop-pop-ret instructions. And I'll explain why they do that in a second. And the next pointer, they'll traditionally set to certain bits of value, which allow them to gain execution control. Now, the reason why attackers traditionally overwrite this with the pop-pop-ret is because when that handler is called, it's called with the prototype that you see in the bottom right-hand corner. And the second parameter of that prototype is the establisher frame. And what that establisher frame actually points to is it points to the address of the exception registration record on the stack that the attacker has overwritten. So in essence, they have a pointer directly into the buffer that they have overwritten with code that they control. And the pop-pop-ret, what that does is it pops the return address, it pops the first argument, and then it pops the establisher frame. And it doesn't pop the establisher frame. It returns into the establisher frame, and that gives them a chance to start executing arbitrary code from a location that they control. So the mitigation to this is Microsoft introduced a linker change into Visual Studio 2003 called safe SEH. And what safe SEH does is, at link time, it builds a table of safe exception handlers, and it includes that statically in the binary. These are exception handlers that it knows are the only valid ones that could be used if an exception occurs. And the way that this works is, if we have a valid exception handler, at the time that that exception is dispatched, it'll go through it and it'll enumerate that table and say, is this handler, in the context of this module, a safe exception handler? And if it is, it will allow that handler to be called and dispatched to that exception handler. If, however, that handler is invalid, then it'll say, oh, well, this is bogus, we can't allow this, and it'll take the steps needed to make sure that that handler is not called. So in essence, this will prevent an attacker from being able to overwrite the handler with an arbitrary address in certain cases. The limitation with safe SEH, however, is that it's really primarily effective if all of the modules in the address space, all of the binaries, have been linked with safe SEH support. If you have any modules in the address space that have not been linked with safe SEH, then it's not possible to make this decision about whether or not the handler, in the context of a module that doesn't have safe SEH, about whether or not that handler is safe, because you don't have any basis of whether or not to make that determination. So what ends up happening is, if an attacker is trying to leverage an SEH overwrite, they'll look for all of the binaries in the address space that don't have safe SEH, and then they'll look for useful instructions within those modules that will allow them to gain control when that exception handler is called. So that's how attackers will actually bypass safe SEH. So a new mitigation, this is an enhanced version of SEH chain validation. It's called SEH-OP, SEH overwrite protection. This provides dynamic protection for SEH overwrites. And this was introduced in Server 2008, and it's on by default in Server 2008, and it's off by default in Vista SP1. This enhancement is provided by the platform. There's no need to relink your binaries, recompile binaries. There's no need to do any of that. It does it behind the scenes for you. And the way that this mitigation actually works is in the exception chain, it'll insert what's called like a validation frame. It's kind of a symbolic marker as the last entry in the exception chain. And every time an exception is dispatched, it will try to walk that chain to make sure that it can reach that validation frame. And the reason it does this is it's trying to make sure that the integrity of the exception handler chain is intact. Because if there was an overwrite, what will happen is, as is illustrated on the right-hand side, the attacker will overwrite the next pointer with some bogus value. And if that bogus value does not retain the integrity of the list, then when we go to dispatch exceptions, we can make the determination that, oh, the integrity of the list is in question. We should not dispatch this exception because there could have been some corruption. There could be an exploitation attempt. So that's the general concept behind how SEH overwrite protection works and actually mitigates SEH overwrites altogether. So to recap, we just talked about GS, safe SEH, and SEH overwrite protection. The sort of invariance that we have at this point is the attacker can no longer overwrite the frame pointer or overwrite the return address for a frame that has a GS cookie. They can no longer overwrite arguments or non-buffer local variables. They can overwrite an SEH like an exception registration record, but safe SEH and SEH overwrite protection will actually prevent it from being called in the event that the exception is dispatched. So all of these mitigations that I've just talked about are primarily focused on preventing stack-based buffer overflows from being exploited. So what about heap-based buffer overflows? So one of the exploits that has been refined over the years is called heap metadata overwrite. And what happens here is an attacker will overwrite some control structure that the heap uses to maintain heap allocations. And oftentimes what you'll see is that these heap control structures, if overwritten in a certain way, will allow an attacker to be able to trigger a secondary memory corruption or gain execution control through those mechanisms. One of the common ones is heap coalesce operation, and that's where you actually try to coalesce two free chunks together. The way that that works in the heap is, if we look at this diagram at the top, we have a traditional heap layout. We have a couple of heap chunks adjacent to one another. When we have a heap-based buffer overflow, what will happen is there will be a free chunk header that we overwrite. And what we can do is that free chunk actually contains a list entry, which consists of a flink and a blink pointer. So if we overwrite those and the heap goes to coalesce those chunks, well, now what happens is part of that coalesce operation is unlinking that entry from the chain. And that unlink operation happens to allow us to overwrite arbitrary memory if we control the address of the flink and the blink pointer. So that's how heap-based control structure overwrite traditionally works. And there are some other techniques that have been refined as well, like exploiting look-aside list allocations and other things like that. So the mitigation of this was to introduce a number of heap hardening mechanisms. The first one was to introduce safe unlinking into heap coalesce operations. And what this does is it makes sure that the entry that is being unlinked meets a certain number of requirements in terms of having as being a valid entry within the linked list that it's being unlinked from. The next one are heap cookies. So this is an 8-bit cookie that is verified when an entry is being allocated from the look-aside list, just to make sure that that look-aside list entry has not been corrupted or anything of that sort. And in addition, heap chunk header encryption has been introduced. So this is the header fields of the heap chunk are XORed with some certain unpredictable value to make it harder for an attacker to be able to overwrite those and gain control through certain mechanisms. So that was a brief overview of some of the heap-based hardening mechanisms. At a more generic level, we can start talking about some of the things that all of the exploitation techniques tend to rely on. One of those things that the techniques rely on is being able to execute data as code. So in this example here, we have our stack layout that we've become familiar with, and then we have our exploit buffer on the bottom. What traditionally happens is the attacker will overwrite the return address with, say, the address of a jump ESP instruction, and when that function returns, it will start executing code that has been injected into the stack. So what this means implicitly is that the attacker is assuming that the stack is executable, that it's allowable to execute code from the stack. So if we could somehow defeat that assumption, we could prevent them from being able to execute arbitrary code in this sense. So that's the purpose of hardware-enforced DEP. And you can think about hardware-enforced DEP, which stands for Data Execution Prevention, as taking advantage of the NX bit that was introduced into x86 processors a couple of years back. And what this allows is it makes it possible to actually mark pages as being non-executable or executable explicitly. And the way that it does this is the platform will actually, when it allocates the stack, it will say the stack is only read-write. It's not executable, such that if an attacker does go and try to execute code from the stack, or if an application itself tries to execute code from the stack, it'll be prevented from doing so. So this prevents attackers from being able to make the assumption that they can execute code from regions of memory that shouldn't really be executable, stack, heap, and so on. So attackers are smart, and they have a couple of techniques that have been developed years past to defeat this. And one of these techniques is called ret to libc, which stands for return to libc, which you can just basically think of it as returning into a function that exists in the address space in some module. So the example here in the diagram, we see that our exploit buffer is composed of some padding. We overwrite the return address with the address of the system function, which is in the MSVC runtime library. And then we set up a fake stack frame. And this fake stack frame is composed of a fake return address and then the parameter that would normally be passed to system. And what this does is when the function returns that we've overwritten the local variable in, when it returns, it actually returns into system as if it were calling it as a function. So now, in essence, what we're doing is we're calling system as a function, and we're able to execute an arbitrary command on the system. And since we're just calling system as if it were a function, we're not relying on the ability to execute data as code. We're just reusing code that already exists in the address space for our purposes. And that's what the purpose of a return to libc attack is. It can actually even be worse. So in Windows, you can use a return to libc attack to actually defeat and reprotect some virtual memory such that even though it was read-write before, you can reprotect it so that it is read-write execute and then return into that buffer. So this is called chaining functions together via return to libc. And the reason why this is possible is because generally across the board, Windows will make use of a calling convention called standard call. And what standard call says is that the caller is responsible for pushing the arguments onto the stack, and the callee is responsible for popping those arguments off of the stack. So, as I mentioned, this actually, standard call allows functions to be chained together when using return to libc. So the diagram at the top will kind of illustrate how this works. So this is our stack, and the arrow is pointing to where the stack pointer is currently pointing to. And right where it's at right now, it's saying this is where the stack pointer is pointing to when the vulnerable function is going to return. So we've done our buffer overflow, we populated the stack with the values that you see in blue, and now we're about to return from that function. So since the stack pointer points where it does, the return address is effectively the address of virtual protect, the virtual protect function. So when this function returns, it's going to return into virtual protect as if it were calling it as a function. So we're doing the return to libc attack. So now we return into virtual protect. So that pops the return address on the stack and shifts it back, and now the stack pointer is pointing to the arguments that will be passed into virtual protect. So when virtual protect is called, it expects the return address to be on the top of the stack and its parameters to be adjacent to it. So we're telling virtual protect that, well, actually, your return address is the address of a jump ESP instruction, and we'll come back to why that's there in a moment. And what follows that are the parameters that we would want to pass to virtual protect, such as the address of our shellcode, maybe the address of some stack-based buffer where we know our shellcode is. The size of the shellcode, so the amount of memory that we want to reprotect. We want to reprotect it to be read, write, and execute. And then we just need some writable address because virtual protect expects to store the old protection attributes in some variable. So we can just pick some writable address anywhere in the address space. So now we execute virtual protect. Virtual protect returns. And when it returns, it's going to return into that jump ESP. And since the stack pointer is currently pointed to where we've now positioned our shellcode on the stack, that jump ESP effectively starts executing our shellcode, and it succeeds because we've changed the protection of the stack to be read, write, execute. So this is a way for us to go from where we were previously had a non-executable stack to an executable stack and start executing arbitrary code. There's also some other techniques that can be done to attack dep. When you're trying to leverage this virtual protect return to libc attack that I just mentioned, it often requires you to have the ability to use null bytes in your buffer that you're overriding with. And that's sometimes impossible if you're dealing with things like string-based buffer overflows, where if you transmit a null byte, that's going to cause a copy to terminate, and you're not going to be able to overwrite as much as you wanted to. So Windows actually comes with a built-in, it's not a public API, but it has an API called nt-set-information-process. And this has been made public with a set process dep policy. And what this allows the application to do is it allows it to change whether or not hardware enforced dep is actually enabled for that process. So at runtime, you can tell the kernel that, hey, I actually don't want you to enable enforcement of non-executable pages. Even if a page says that it's not executable, I don't want you to enforce it. So that's what this mechanism allows you to do. So we can use the same style of attack, the return to libc attack, to execute this nt-set information process and actually cause the kernel to disable the prevention of executing from non-executable pages just across the board. And once we've done this, we can just execute from a page even if it's marked as non-executable. So that can be an effective way to defeat this. Now the mitigations for this. The technique I just talked about with nt-set information process, dep does come with the ability to mark the execution flags as permanent for a process. And what this means is when it's marked as permanent, it's not possible for the process to make any subsequent changes to the execute flags. So it's basically set in stone from that point, and then there's no way for the process to change it. However, this doesn't actually mitigate the technique that I talked about previously, which is the virtual protect technique. It's still possible to change the page protections to be executable if they originally were not, and execute code using that mechanism. So there's a common thread about all of these things. Does anybody want to take a guess at what that common thread is? All right. Well, the common thread is this. Each of the techniques that I've talked about generally relies on some knowledge of the address space. So for instance, when we were overriding the return address, we needed to know what address to override it with so that we could execute code. You know, we needed to know the address of our shell code, we needed to know the address of a jump ESP, and so on. When we talked about the SEH overwrite, we had the same sort of problem. We need to know what address to overwrite that handler with so that when the exception handler is called, it's going to execute our arbitrary code. In the case of a heap overflow, we need to know the what and the where address that are going to be used to do the coalesce operation. And when we're doing a return to libc, for instance, if we're going to do the return into virtual protect, we need to know the address of virtual protect. So all of these are making assumptions about where things live in the address space. So the big question is, what if we were going to make the address space unpredictable? You know, what effect would that have on all these exploitation techniques? And this is where we come to the mitigation of ASLR. ASLR stands for Address Space Layout Randomization. And what this does is this basically randomizes where things live in the address space, such that if you sat two Vista machines side by side, the location of virtual protect would be different between the two of them. And what this means is if an attacker is trying to write an exploit and their exploit relies on knowing the address of virtual protect, then maybe they'll guess right and they'll get it right for one machine, but they might not get it right for a bunch of other machines. So this is reducing the reliability of all these exploitation techniques by making it much more difficult for them to be able to guess successfully where things live in the address space. So this mitigation was introduced in Vista and in Server 2008, and right now it currently provides 256 bits of entropy, which doesn't sound like a lot, but it really is very effective at actually offering protection. However, this mitigation requires executables to have been linked with the dynamic base flag to indicate that, yes, I support ASLR, and this is to encourage app-compat, to make sure that we don't introduce compatibility issues by just randomizing everybody out from under them. Now, as we've seen, each of these mitigation techniques tends to have a problem. You know, it's not a panacea in and of itself. Each of them has maybe a little corner case where we can defeat it and bypass it. And ASLR is no different. So one of the techniques that you can use against ASLR, specifically against Windows implementation of ASLR, is called a partial address overwrite. And the way that this technique works is since ASLR in Vista only introduces entropy into the top 2 bytes of an address, so if we think about an address, it's stored in 4 bytes. only the top 2 bytes are going to have entropy introduced at some level. The low order 2 bytes will have no entropy introduced. And this has to do with the implementation detail of Windows, the system allocation granularity. So what this means is if you control an overwrite and you only overwrite the low 2 bytes, then you can effectively pivot to anything within that 16-page region. You aren't affected by ASLR at that point. So this is a method that can be effective at evading ASLR, but you're constrained to being able to make use of things that are within the same 16-page region as the address that you're overwriting. Another problem that you can run into are non-relocatable or fixed executables. So in this diagram here, we can see that this app.exe is basically located at the same address across multiple boots of the operating system. And this is because, in many cases, executables aren't linked with the flags necessary to introduce relocations into the binary. So they're linked with /fixed:"yes." Or there may be some other situational issues, such as there was a presentation this summer at BlueHat by Mark Dowd and Alex Odoroff that talked about how you can use .NET IL-only assemblies and take advantage of a certain implementation flaw to force those assemblies to be located at a fixed address in the address space when they're loaded into Internet Explorer. So these are different ways in which, if you can make something be loaded at a fixed address in the address space, then ASLR isn't really providing you a lot of value because its whole purpose is to randomize where things live in the address space. So ASLR is primarily effective if everything in the address space has been randomized. There's nothing that allows the attacker to make an assumption about where things live. There are some other issues with ASLR. So one thing that people might have thought about already is brute force. So you could potentially, given the vulnerability, you might be able to brute force by guessing a bunch of different times until you get the right address that you're trying to hit. And it's possible. On Windows, I personally consider it a little less likely because there was the foresight of introducing things like the Vista Service Restart policy. So if a service crashes a certain number of times, it won't allow itself to restart until somebody takes a look at it. And also, Windows doesn't really have the concept of things like forking daemons, whereas on Unix platforms, you have the concept of forking daemons, which you can just keep spawning off new processes, and even if they crash, it doesn't affect the parent process. So in Windows, it's more the case of where if the attacker gets something wrong, they guess the wrong address, the process is going to crash. Now, there's one catch, and this is something that, unfortunately, I've seen a couple of times in code where folks will implement these catch-all exception handlers. You know, they'll swallow exceptions and maybe log an error or something like that, but they'll allow the application to keep executing. And this has the nasty effect of, if somebody is trying to exploit a vulnerability in your code, even if they guess the wrong addresses, they throw an access violation and all these other things, by catching this exception and allowing the process to continue, you're giving that attacker multiple chances to try to exploit that vulnerability, where otherwise the process would have crashed. So in general, I would encourage folks, don't swallow exceptions. You know, allow them to bubble up. Even if you're going to crash, it's better than exposing this security flaw of allowing people to brute force and whatnot. Another problem you can have is, and this applies to GS, this applies to ASLR, anytime you have something that's supposed to be secret from the attacker, like the GS cookie or where things live in the address space, you don't want that information to get exposed to the attacker. So one problem you can have is an information disclosure, where maybe some behavior of your application allows the attacker to read from certain areas of memory or what have you, and from that they're able to glean, oh, well, this binary lives at this location in the address space, or here's what the GS cookie is, and things of that sort. So if any of those secrets get leaked to the attacker, it significantly weakens these mitigations. So let's recap. I talked briefly about the heap, DEP, and ASLR. So what this means now is the attacker can't leverage heap metadata corruption, because now we have some sanity checks in the heap to prevent that from being possible. Now, it's still possible, and this remains an unsolved problem, for the attacker can still overwrite other allocations in the heap, such as, you know, maybe an adjacent class has been allocated on the heap. And if those heap allocations contain function pointers or things of that sort, and those function pointers are called, then it may still be possible for them to execute code through that mechanism. But at that point, the attacker is relying on app-specific, vulnerability-specific layout and qualities of the heap. And it's not something generic, whereas taking advantage of a heap coalesce tends to be a fairly generic technique. From DEP, we can now say that the attacker can't execute code as data in the general sense. And with ASLR, we can say, well, the attacker cannot make address-based assumptions when they're writing their exploit. So those are the mitigation techniques that I was talking about. Now I wanted to take a step back and kind of show you what the chronology was for this process. If we go way back to 1996, there was sort of the landmark paper that most folks cite when they talk about buffer overflows, which was Alef1's Smashing the Stack for Fun and Profit. This was published in 1996. Then we had a period of time between 1996 and 2002 where heap-based buffer overflows, the techniques that were used, the heap coalesce, the safe unlinking, things of that sort were refined. And many of these techniques were refined on platforms other than Windows, but it just so happens since Windows and other platforms use the same architectures, x86 in this case, a lot of those techniques can be applied across the board. So it wasn't until 2002 where Microsoft actually introduced the first support for /GS in Visual Studio 2002. And if we look shortly after that in 2002, there was a bypass technique released for GS. And this is the one that I mentioned where you could overwrite the local variables or you could overwrite other parameters in the stack frame. And if those were used before the function returns, that allows you to sort of evade the GS protections. Then later on in 2003, Visual Studio 2003 was released. And in this release, we have enhancements to GS, and we also have the first introduction of safe SEH. So later that year in 2003, there was the first public paper that I'm aware of that talked about how to make use of an SEH overwrite to actually defeat GS or just to be used in a general sense. And then later that in 2004, there were some refinements to heap-based overflow techniques, some advancements in that area by Matt Conover and Oded Horowitz. Later in 2004, we saw the first release of XPSP2, and this was sort of a major milestone for Windows. This was the first time that the full platform was compiled with GS, linked with safe SEH, and data execution prevention was introduced in the platform. So this was a huge milestone for Windows in terms of the mitigations that I've talked about today. In 2005, there was a paper released talking about how to do the DEP bypass involving NT-set information process. The technique that I described about using virtual protect, that technique had already been refined back in the later years, primarily on the Linux platforms because it was more applicable there. Later on in 2005, we had the release of Visual Studio 2005, and this was another enhancement to GS. In 2006, we had the first release. We had the release of Vista RTM, and this gave us ASLR. So now we have ASLR. The platform's compiled with GS, linked with safe SEH. It's all the binaries are opt-in, or the majority of the binaries are opt-in to ASLR and DEP by default. So again, this is another major milestone for the mitigations in Windows. And we can say pretty strongly that Vista is a very solid platform in terms of the mitigations and the countermeasures that it provides to prevent exploitation. And in 2008, Server 2008 was released, and this included the SEH overwrite protection, which I mentioned earlier. This is on by default, so now it's much more difficult for attackers to be able to take advantage of an SEH overwrite to exploit and execute arbitrary code. And finally, there was a paper released this summer at BlueHat, as I mentioned, from Mark and Alex, that talked about some techniques that you could apply in the context of a browser to defeat ASLR and DEP. Such as the .NET IL-only controls and a couple other techniques. So these are some other, so we can see that the process is still continuing there. So let's recap the current mitigations. The Windows binaries built with GS, linked with safe SEH, DEP and ASLR compatibility are opt-in for the binaries. The heap mitigations are active, so safe unlinking, heap cookies, header encoding, and so on. DEP is enabled by default, ASLR is enabled, and SEH overwrite protection is enabled by default in Server 2008, and it's disabled on Vista SP1 primarily for app compat concerns. So call to action for everybody. I encourage everybody to opt into these mitigations. These are things that you essentially get for free that provide you protection for vulnerabilities that you may not even be aware of. These are things that are going to make it that much harder for an attacker to try to exploit a vulnerability in your software. And as we've seen, attackers are much more opportunistic. They want to go to where things are the weakest. So that's why over the past years we've seen this trend shifting away from focusing on Microsoft to focusing on third parties, where adoption has been much slower for these mitigations, or they just aren't able to take advantage of them. And that's that's for a number of reasons. I mean, SDL and a number of other things. But one of the things, too, is the fact that the platform now has all these mitigations, and vulnerabilities in the platform are that much harder to exploit that it's really just not worth the attacker's time to focus on something that's really hard that maybe if they spent a long time working on it, they'd be able to take advantage of it. But, if they spent 5 minutes looking at this other thing that doesn't have any mitigations, it's very cookie cutter, very easy for them to do. So I encourage everybody, opt into these mitigations, take advantage of them. They're just adding tons and tons of value. And the other thing, too, that I would mention is these mitigations, while they do have issues independently, there are ways that you might be able to bypass them. All these mitigations working in concert with one another is really what's sort of bringing it all together. They're covering each other's back, and they're providing all that value. So don't just pick and choose which mitigations you're going to opt to. Opt into all these mitigations because they really do add a ton of value when they're working in concert with one another. The other call to action that I would say is challenge assumptions and avoid paralysis. And what I mean by this is some of the major concerns, and they're rightfully so, it's right to have these concerns, that people have around application compatibility and performance. For the most part, these mitigations try to be as non-intrusive as possible. They try to be not noticeable. It's just things operating as normal. But it is possible to have app compat issues, and it is possible to have performance issues. But I would encourage everybody, don't assume that you're going to have these issues. Go and enable these mitigations, test it, try to track it down. If it is these mitigations, at that point, make the call of, what do we need to do? Maybe we need to disable this, or what can we do to make it so that this isn't an issue? Because these mitigations add so much value that it's really worth working through these app compat, these performance issues, just to provide that extra protection for you in the event that your code does have a vulnerability. So those are the things that I would encourage everybody to do. And these are things that if you're following the SDL, these are already an SDL requirement, so you should be following if you're doing that. So I have a number of references here. I don't expect everybody to be able to read that, but with that, I'll open it up to questions. So any questions?
Very much, Matt.
Thanks.